Spaceflight-Associated Neuro-Ocular Syndrome, or SANS, represents a severe, mission-limiting physiological risk for astronauts during long-duration interplanetary transit. SANS causes profound physical deformation of the eye itself. Astronauts experience optic disc edema, globe flattening, and hyperopic shifts that directly degrade their visual acuity. The current scientific consensus links these structural deformations to the loss of gravity. Without Earth's downward pull, bodily fluids experience a cephalad shift. They continuously pool upward into the head and eyes. VAX research identifies a localized mechanical failure working alongside this fluid shift to compound the damage. To understand this failure, we look to the glymphatic system, a macroscopic network responsible for draining interstitial fluid and metabolic waste away from our neurological and ocular tissues. This biological drainage requires two mechanical forces to function: the pulsing pressure of your arteries and the constant downward vector of gravity. On Earth, these forces flush the system. In microgravity, that downward force disappears. Metabolic waste completely stagnates around the optic nerve. This accumulating fluid places immense physical pressure on the tissue, directly triggering the cellular stress and structural swelling defining SANS. Stopping this structural damage requires a physical intervention. We need a way to artificially replicate the mechanical pumping force of gravity and actively flush the eye from the outside in. This is the premise of echo-drain, a proposed physical countermeasure designed to clear out this hypogravity-induced stagnation. The intervention relies on applying targeted, low-frequency acoustic waves, specifically micro-ultrasound, directly to the affected ocular tissues. When these waves pass through a liquid medium, may generate a phenomenon known as acoustic streaming. This creates an artificial pressure gradient that actively pushes the stagnant fluid and trapped waste particles away from the optic nerve head. Operating acoustic devices inside biological tissue requires strict safety constraints. First, the frequencies must remain low enough that they avoid inducing cellular cavitation, which would tear the delicate fluid matrix apart. Second, the energy output must be carefully modulated to prevent any localized heating from causing thermal damage to the surrounding eye structures. To meet these parameters, the system utilizes highly miniaturized piezoelectric transducers. These solid-state emitters are programmed to deliver the precise ultrasonic frequencies required to induce streaming without crossing the threshold for tissue damage. By applying these calibrated microacoustics, we can artificially stimulate the exact fluid-clearing mechanics that gravity provides on Earth, mitigating the pathology of SANS at the cellular level. Testing this hypothesis on the International Space Station requires strict adherence to agency safety guidelines, which mandate the use of living, non-human biological models. The solution is a 3D bioprinted Optic-Nerve-on-a-Chip. This accurately replicates the tissue architecture where SANS initiates. The central hydrogel matrix is seeded with living retinal cells and fed by fluidic channels. Adjacent to this is the miniaturized piezoelectric transducer, projecting acoustic energy into the tissue. For orbital flight, this chip assembly integrates into a multi-layered commercial hardware platform. The middle layer houses microfluidic pumps, forcing fluid pressure into the chip, mirroring an astronaut's cephalad fluid shift. Above the matrix sits an automated fluorescence microscope to capture continuous morphological data. The overarching constraint for this apparatus is scale and autonomy. The pumps, the acoustics, and the optics must all operate completely automatically inside a shoebox-sized cube lab without any crew interaction. The resulting payload packages both the biological cause of SANS and the diagnostic hardware required to test its cure into a single, fully autonomous system. Once installed aboard the ISS and powered on, the 30-day experimental cycle begins. The microfluidic pumps initiate the process by injecting a solution of fluorescent tracer nanoparticles directly into the biological tissue construct. These glowing particles act as a proxy, simulating the buildup of toxic metabolic waste that naturally occurs within the extracellular matrix. Control group chips are subjected only to continuous fluid pressure, allowing researchers to observe baseline microgravity stagnation as fluorescent waste pools. Simultaneously, transducers activate on the experimental chips, testing if pulsed acoustic streaming successfully forces the trapped nanoparticles out through drainage channels. Throughout this process, the onboard microscope logs these clearance rates daily and downlinks the temporal data to the research team back on Earth. Quantifying this exact rate of nanoparticle clearance in the harsh environment of orbit will definitively prove whether targeted acoustics can function as a reliable physical pump for stagnant biological fluids. A core mandate of this research grant is that spaceflight testing must yield tangible translational benefits for Earth-based healthcare. The most immediate commercial pathway for EchoDrain targets the treatment of glaucoma. Glaucoma affects over 76 million people and is the leading global cause of irreversible blindness, a condition driven primarily by elevated intraocular pressure. If this acoustic intervention proves it can safely clear ocular fluid in orbit, the hardware can be miniaturized into a wearable device, embedding the micro-ultrasound emitters into an ergonomic sleep mask. Patients could wear this mask at night to passively stimulate fluid drainage and relieve internal eye pressure, bypassing the need for invasive ocular surgeries or a lifetime of restrictive chemical eye drops. But the potential applications extend well beyond the eye, reaching into the treatment of neurodegenerative diseases like Alzheimer's. The connection lies in the anatomy. The human brain relies on the exact same macroscopic glymphatic network to flush its own metabolic waste. During deep sleep, this paravascular system expands to flush out toxic proteins, specifically the amyloid beta plaques that drive Alzheimer's. Validating that acoustic waves safely enhance this biological clearance in microgravity provides the foundational data to develop non-invasive therapies stimulating plaque clearance in the human brain. EchoDrain represents a rigorous orbital proving ground for advanced fluid dynamic medical devices capable of treating millions